In the diagram, PQ and RS are diameters of a circle with radius 4. If PQ and RS are perpendicular, what is the area of the shaded region? I'm going to call this region here A, and this region, of course, will also be A. So the area of the shaded region will be equal to the area of the full circle, which is pi r squared, minus 2A. So if we can figure out A, this will be no problem. So let's first concentrate on figuring out A. And how do we do that? Well, the first thing I'm going to do is sort of connect PR and SQ. And I did that to sort of show that, not that it really was necessary, but that this is kind of like a square, right? I think it is a square. And the key thing here is that there's one line in this question that really helps. It's this one right here. PQ and RS are perpendicular. That's very helpful. Why? Because if PQ and RS are perpendicular, then that means this is 90 degrees right here. And therefore, that means that this triangle is going to be very easy to figure out in terms of its area. So A will be the circle pi r squared divided by 4, because this segment of the circle is basically a quarter circle, because that's 90 degrees, minus the area of that triangle, which will be, of course, 1/2 base times height. But the good news is that the base is just the radius of the circle, which is 4, and the height is also 4. So 1/2 4 times 4. So pi r squared, well, r is 4, so that's 16 over 4, and this looks like 16 over 2. So this becomes 4 pi minus 8. And there we go, we just got A, so we can now calculate area of the shaded region. Pi r squared, well, r is 4, so we have 4 squared, minus 2 times A, so 4 pi minus 8. So this becomes 16 pi minus 8 pi plus 16, and therefore this is 8 pi plus 16. 8 pi plus 16 is choice E for number 22. 3 friends are in a park. Bob and Clarice are standing at the same spot, and Abe is standing 10 meters away. Bob chooses a random direction and walks in this direction until he is 10 meters from Clarice. What is the probability that Bob is closer to Abe than Clarice is to Abe? Well, initially, we have some scenario here where Bob and Clarice are here at this point, and 10 meters away is Abe. And then Bob will start to walk 10 meters in some direction. Now, we don't know where he's going. Maybe he's going here, maybe he's going there. But one thing is for sure, that he's going somewhere that would create a circle, right? Because he's always 10 meters away from where he originally was, which was with Clarice. So let's just say he's here. I don't know where he's going to be, but let's just say he's there. And let's draw in that circle. All right, perfect. So what I've done is I've said that he's walking 10, and he's going to end up there. So let's just label it 10. 10 there and 10 here. Now, the thing is, he's going to be there, but he could be anywhere on the circle. He could be here, he could be there, and so on, right? He could be anywhere. I don't know where he's going to be. But they have given me a criteria that wherever he ends up, they want the distance from him to Abe, which I guess would be that distance, to be less than the distance from Clarice to Abe. Well, currently it doesn't seem to be the case at all. So let's just write that here. We want the distance from B to A, which is BA, to be less than the distance from C to A, which is Clarice to Abe. And C to A we know is 10, so basically we'll want the distance to be less than 10. Okay, so I don't think it's going to be here. It's probably going to be, I don't know, maybe here perhaps, where Bob is going to be. And if Bob is there, then his distance, if I draw a line, would be from there to there. All right. And then what I'm going to do is I'm going to connect C to B like that. So now, what I'm interested in is this angle here. Angle theta. And if I can figure out that angle, that's going to help me a lot. But before I do, I also want to point out that this identical situation could happen here. Bob could be here also. And therefore, that distance would be like this, from B to A. So theta can be there as well. So as long as Bob is in between that part of the circumference, we're good. As long as BA is less than 10. So how do I make sure that BA is less than 10? Well, looking at this graph, the distance from there to there is just the radius, so that's going to be 10. And the distance from here to here has got to be less than 10. So 10 is the sort of upper limit, right? And if it's less than 10, then he'll end up here. So this triangle helps me figure out that theta. Why? Because if you notice, it's equilateral. So that means all of these angles are 60, 60, 60, and 60. So that means this whole range is 120. As long as he is within this range, so it would be between there and there on the circumference, he will be in a position, let's just say here, where his distance to A will be less than 10. So I hope that makes sense. Well, what percentage of the circle is 120 degrees? Well, I divide by the total number of degrees, which is 360, and that just reduces to 1/3. So that is the probability of this question. So number 23, the answer is B. A semicircle of radius 8 rocks back and forth along a line. The distance between the line on which the semicircle sits and the line above is 12 centimeters. As it rocks without slipping, the semicircle touches the line above at 2 points. When the semicircle hits the line above, it immediately rocks back in the other direction. The distance between these 2 points in millimeters is closest to. So here is a diagram that illustrates what the question stem is talking about. And you'll notice that the dotted line here is the semicircle in its original position. And then what this diagram shows is that the semicircle then is tilted so that it is now in this position. And when that happens, it hits the line above at point Q. And because of the symmetry of this diagram, when it rocks back in the other direction, it will probably hit around here. But we don't need to be concerned about that yet. We just need to figure out this distance from Q to P, and then double it, and we will get the answer to this question. So let's begin. The first thing you'll notice is that the center of the semicircle originally was right here. But when it's tilted, that center is now here, the point that is labeled O. So therefore, the distance from O to Q is the radius. And that, they tell you, is 8 centimeters. So I will put 8 right there. Now we need to figure out as many distances as possible. So the next one that you can figure out pretty quickly is O to Z, that distance right here. You know that from this point till the bottom is just the radius, and that's going to be 8. And they tell you that the line above is 12 centimeters. So that means that P all the way to the bottom is 12. So that means that this distance is 12 minus 8, which is 4. And therefore OZ will also be 4. So let's draw this triangle QZO on the side here to avoid making this diagram messy. So here is Q, here is Z, and here is O. And we figured out that that's 4. And this is, of course, just the radius, so that's 8. And this is a right angle. So now, using Pythagoras, I can figure out QZ. QZ squared is going to be, add that to 4 squared is equal to 8 squared. And therefore, QZ squared is going to be 64 minus 16, which is 48. And therefore, QZ is root 48, or 4 root 3. So that takes care of QZ. Now, we need to figure out QP, the distance from here to here. So how do we do that? Well, we have QZ. If we can figure out the distance from P to Z, then we will be able to solve this question. So QP is going to be equal to QZ minus PZ, like that. So we are now going to try to figure out the value for PZ. Well, QZ we just calculated as 4 root 3. Now I want you to concentrate on this triangle here. Notice the side lengths. If you look at the side lengths, and in particular look at the ratio, you'll notice that the ratio of the side lengths are 1, 2, and root 3. And because that is the ratio of the sides, this is a 30, 60, 90 triangle. This is 30 degrees, and this is 60 degrees, and that we already know was a right angle. Now, how does that help us? That helps us, hopefully, figure out PZ, since that is what we're trying to figure the distance of. But how does that help us? Well, look back at this original diagram, and let's fill in the 60 degrees. That 60 degrees is right here, correct? So that means this angle here is 30 degrees. Okay? Now, pay close attention. This semicircle moved from here to here. Did you notice that? It was here, and when it rotated, it went up to here. How many degrees is that? It is 30 degrees. So that means this semicircle rotates 30 degrees when it goes from this point to point Q, which is the point that touches that top line. And that 30 degrees is very important because it tells me that the distance from here to here, x to y, is essentially a fraction of the circumference of that circle. What is the fraction? 30 degrees over 360 degrees. So that is the key to the question. xy, this distance that this semicircle travels, initially it was right here at x when I was touching the base, but then once it tilts, it touches the base at y. And we want to know what is the distance between x and y. Because x and y are similar to p and z. If we can figure out the distance xy, xy is the same as pz. And that is what we want to figure out. Well, xy, as I previously mentioned, is calculated by the fact that this semicircle tilts 30 degrees. So 30 degrees divided by 360, which is the full way around, that is the fraction of the circumference that travels from x to y. All right, so the distance from x to y is 30 over 360 times the circumference of that circle. Now, 3 over 360 is 1/12. The circumference of the circle is pi times 2 times the radius. So this just becomes pi over 6 times the radius, and the radius of this circle is 8. So this looks like 4 pi over 3. All right? So that is xy, but remember xy is the same as pz. So therefore pz is equal to 4 pi over 3. So going back to this formula right here, qp is equal to qz, which is 4 root 3, minus pz, which is 4 pi over 3. And if you take out your calculator and you get an exact value in decimals, you will get 2.741 approximately. Now remember, QP is only half of the distance we are looking for, because if you go back to the question, you'll see that when this semicircle rocks back and forth, it will touch the top line at 2 points. And therefore, the other point is going to be somewhere, let's say here. And because of the symmetry of this diagram, the distance from P to that point is the same as the distance from P to Q. So since we got QP, we can just multiply QP by 2 to get the total distance. And therefore, QP multiplied by 2 is approximately 5.483 centimeters. And if you multiply by 10 to get millimeters, you get about 54.83 millimeters. And if you round that to the closest integer, it will be 55. And therefore, number 25, the answer is A. The circular window shown in the diagram has 9 panes of equal area. The inner circular pane has a radius 20 centimeters and the same center O as the outer circle. The 8 lines separating the outer panes are of equal length, x centimeters, and all, if extended, would pass through O. What is the value of x to the nearest tenth? So, first and foremost, what we need to do is join these 2 lines like that. And we'll label that R right there. That will be the radius of that small circle. And they tell us what is R. They tell us it's 20. So there we go. That piece of information will come in handy because we can calculate the area of that small circle. This one right here. That small circle in the middle. So it will be pi times 20 squared, which is 400 pi. Now, this sentence is very important. 9 panes of equal area. So that means that each one of these is equal in terms of its area. These guys that all have the same shape and this circle. So that means each of those guys that looks like this is also equal to 400 pi. So how many of those do we have? Well, they tell you there's 9. Well, there's 8 of these, and then there's a 9th shape that's in the middle. So the total area is 9 times 400 pi, correct? And that's 3600 pi. And that is equal to pi big R squared, where big R is the radius of the big circle. So it would basically be from here to here. We call that big R. And we can solve for this. Pi big R squared, well, the pi's cancel first of all. So you're just left with R squared is equal to 3600. And if you take the square root, R will be equal to 60. Okay, so R is 60, that's small r, and then this length here is x. So that means small r plus x is equal to big R. Small r is 20, big R is 60, and therefore x is 60 minus 20, which is 40. Exactly 40. So number 21, the answer is A. A wheel with radius 1 is rolled in a straight line through one complete revolution on a flat horizontal surface. How many meters did the center of the wheel travel horizontally from its starting location? Okay, let's draw a little diagram here. We've got one circle and then the exact same circle. Something like that. And we are asked essentially to figure out the distance from the middle to the middle, like that, as this wheel or circle, it's a wheel actually, moves along. So that red line is what they want you to figure out. Well, this question basically says that the wheel is turning one complete revolution. So that means that along the floor of the, what are they calling it? Flat horizontal surface. Flat horizontal surface. It's going to travel from here and then eventually end here. Now that distance represents one complete revolution. It represents the circumference, c. So the answer to this question is c. But those are not represented in the answer choices. We want an actual numerical value. The circumference is how far this circle will travel. Well, we know that the circumference is equal to pi times diameter. Diameter is 2 times the radius. And the radius they give you is 1. So there you go, 2 pi. And that's it for number 23. They gave you a little bit of a break on number 23. So the answer is C.